The next concept I want to talk about is a p-value. And a p-value is the probability of observing a sample as or more extreme as the observed sample, that is the sample that you actually have in your study. Due to random sampling, if the null hypothesis is true. Right, so there's a lot in here, but these p-values, these probability values, are an essential part of any kind of hypothesis testing that you do with inferential statistics. In the introduction to the z-test, I talked about how you can use the critical region and z-critical values to decide whether or not to reject the null hypothesis. And that's something that you'll do in classes like this. But when you're doing analyses outside of a class like this, you don't actually compare z-critical values with z-statistics. Instead, what you do is you get a p-value from the statistical program that you use, and you compare your p-value with your alpha of 0.05. So this is the probability of observing a sample as or more extreme than the one you observe. So a really small p-value is a really unlikely sample if the null hypothesis is true. So for example, if we do an analysis and we get a p-value of 0.04, well, this only happens 4 out of 100 times. And we've decided that we're going to reject the null hypothesis if things are so unlikely they happen less than 5 out of 100 times. So this is more extreme than this. So if our p-value is smaller than alpha, we reject the null hypothesis. If our p-value instead were 0.08, this is not so unlikely if the null hypothesis is true. It's larger than alpha, so here we can't reject the null hypothesis. We'd fail to reject the null hypothesis, and we would decide that our research study is inconclusive. To illustrate how p-values work, we're going to use the same scenario that we just used for the z-test. So our null hypothesis is that SUU men are as tall as American men, and we know that American men are on average 70 inches tall, and the standard deviation of American men is 4 inches. And what we'll do is we'll go through some different observed samples, and we'll talk about how they have different p-values and how that influences the decisions you would make about whether or not you reject the null hypothesis. So to understand p-values, we want to start off the same way we did with the z-tests. Really, it's the exact same process, but you're using a different approach to deciding about whether or not to reject the null hypothesis. The p-value approach rather than the critical region approach. So we'll start off drawing our population distribution, which assuming the null hypothesis is true, and remember this is individual American men, and so it's going to be something like that, normally distributed with a mean of 70, standard deviation equal to 4. And in this case, since I'm going to have various samples, the next thing I'm going to do is draw the sampling distribution. And this is the kind of samples you expect if the null hypothesis is true, right, due to random sampling. And these are sample means in this case, and these are expected samples if the null hypothesis is true due to random sampling. So this will be a normal distribution that's shrunk in. Its mean is going to be 70. Its standard error, which is also its standard deviation, is going to be that formula. So I'll just rewrite that down here. So it's 4. We'll go with, in this example, sample size equals 100 again. So we'll have 4 divided by the square root of 100, 4 divided by 10. 4 divided by 10 is 0.4. All right, so this is the scenario we'll start with, and then what we'll do is consider we'll calculate p-values for different samples that we observe and look at how that affects whether or not we reject the null hypothesis. So for our observed sample, distribution, all right, this is individuals. I'm just going to draw this as a normal distribution to keep things simple, and because we're going to include different values for the sample mean. We'll start off with the sample mean that we used before in our earlier example. We'll call the sample mean 1. This is the sample mean of 71.2, and we'll keep the sample standard deviation the same at 4.2. The sample standard deviation doesn't impact the calculation of p-values for z-tests anyways. Now, before I do a p-value example, I want to really quickly refresh you on how the critical region approach worked. So recall we have our alpha of 0.05. That's how extreme the areas are on the end, where we're going to reject our null hypothesis of our samples there. And we split this 0.05 on the two sides evenly because it's a symmetrical distribution. And we looked at the z-table, and the z-score, that is the z-statistic on this distribution, who's got an area of 0.025 beyond it, was plus 1.96, or below negative 1.96. And so our z-critical values were plus or minus 1.96. And then when we calculated the z-statistic of our sample mean, that is the z-score of our sample mean on this distribution, we compare that with our z-critical. So we can do z-statistic equals our sample mean minus the mean of the sampling distribution divided by the standard deviation of the sampling distribution, which was 71.2 minus 70 divided by 0.4. And our z-statistic is 3.0. So remember, 3.0 was more extreme than this, right? This is about a z-score of 2, so this is a whole nother standard deviation over. So our sample mean is someplace over there. Our z-statistic is more extreme than our z-critical, so we reject the null hypothesis. We decide that this sample is so extreme that it probably didn't come from this population. Instead, it came from a population of taller men. That is, SUU men are a population that is, on average, taller than American men. So that was how we worked through this problem when we used the critical region approach. Now I'll switch over and use the p-value approach for this exact same example, so you can see how the p-value is calculated and how the decision process is a little bit different. But you'll always have the same decision about rejecting the null hypothesis or not. They're mathematically interchangeable approaches. So for the p-values, we no longer need these critical z-statistics. So we can get rid of those. We still need our sample mean. And we don't need these. So to calculate a p-value, it's really a version of what we did already when we went through doing z-table problems. So what we're going to do is we're going to figure out the area beyond our sample mean on this distribution for one side, And then because we're doing a two-tailed test, so that's how extreme it is on one side, but we're interested in both sides. So we're going to also calculate the area beyond that z-score on this distribution on this side. We're going to take those two areas, we're going to add them together, and that's our p-value. So we'll do that for this example here. So we need to get our z-score of this mean on this distribution, right? That's a z-statistic, right? So this is the exact same start as the last approach. For the critical region. So we got 71.2 minus 70 divided by 0.4. So our z-statistic equals 3.00. So now we know we're interested in a z-score of 3, because the z-statistic is a z-score on this distribution. And what we want to know is what area of this distribution is beyond a z of 3. So you go to your z table, you find a z of 3 on there, 3.00, because that's exactly what this is. And you find out what's the area of the normal distribution beyond a z of 3. And I did that earlier, and I found that that value is 0.0013. So this colored in area is just a little bit, 0.0013. It's a very small part of this overall curve. It's a symmetrical distribution, so when we look up the other half, because we're interested in extreme scores on either side, it's a symmetrical distribution, so the area beyond 3 on this side is also going to be 0.0013. So we want to add them both together. And that is our p-value. So for this sample data, the p-value is 0.0026. So I'm going to rewrite that up here. P equals 0.0026. So we can interpret this as the probability of getting a sample this extreme, if the null hypothesis is true due to random sampling, you get this extreme if a sample less than about 3 in 1,000 samples. It's way less than 1 in 20, which is what our alpha is. So whenever our p-value is smaller than our alpha, like it is here, whenever our p-value is smaller than our alpha value, like it is here, we reject the null hypothesis. So in this case, we do reject the null hypothesis that SUU men and American men are the same height. And we would interpret these results as SUU students are from a population of men that are taller than American men. If our p-value were 0.05 or larger, we would fail to reject the null hypothesis, and we would decide that our results are inconclusive. So now we'll do another example. We'll say sample 2, and its mean is 70.8 inches, and sample standard deviation is, we'll just keep it the same, 4.2. But for a z-test, the sample standard deviation doesn't influence the test anyways. So now what we're going to do is we're going to calculate the p-value for this observed data. Right? So everything else is the same as it was before. All we've done is changed what the observations were like. So the p-value, to calculate the p-value, we need to find out the z-score of our sample mean on this distribution. A z-score on this distribution is called a z-statistic. And so we want to find out the location of our sample mean on this distribution. So we'll just plug in the mean and the standard deviation for this distribution here. All right. Our sample mean was 70.8 minus 70 divided by 0.4. So that's going to be 0.8 divided by 0.42. So here we have a z-statistic equals 2. All right, so we can go to our z table, right? Remember, a z statistic is a z score. This is a normal distribution, so we can use the z table to figure out what area of this distribution is beyond a z score of 2. Right, so a z score of 2 might be someplace around there. So color in something like that. All right, we'll go to the table, we'll find a z score of 2 and look for the area beyond it. And I did that earlier, and I got a value of .0228. So about 2% of this overall area under this curve is beyond a z of 2. We're doing a two-tailed test. We're interested in if our sample mean of SUU men were really tall or really short. So we're actually going to also look at z equals -2 and the area beyond that. It's a symmetrical distribution, so this will be the same, .0228. So to calculate our p-value, we need to add both sides together. .0228 plus .0228, 6540. So our p-value, or p equals .0456. So our p-value is .0456, and we compare our p-value with our alpha. Remember, our alpha is .05, and if our observed sample has a smaller p-value than alpha, you reject the null hypothesis. .0456 is smaller than 0.05, so in this case we reject the null hypothesis that SUU men are the same height as American men. Our sample had a higher mean than American men, and so we interpret these findings as indicating that SUU men are taller than American men. And so to interpret this p-value again, this is the probability of observing a sample as or more extreme as the one we did due to random sampling when the null hypothesis is true from this distribution. Right, so you can, this p-value is the area that I've colored in here beyond the observed z statistic. Right, so I've just added the area on this side to this side, add those together, and that's my p-value. So I want to do a third example of calculating a p-value. So I'm going to call this sample 3. And I'm just going to switch this mean over a little bit. 70.4. So notice each time I've switched these sample means, I've drawn them in closer and closer to the population mean, and therefore the mean of the sampling distribution. Right, so we want to calculate the p-value for this observed sample. So again, we need to calculate its z-score on the sampling distribution. The z-score on the sampling distribution is called a z-statistic. And we want to calculate how many standard deviations our sample mean is away from the mean on this distribution. So we use our modified z-score formula, modified just with the appropriate symbols for that distribution. So our sample mean is now 70.4. 70 is the sampling distribution mean. Its standard deviation, its standard error is 0.4. So now we have on top 0.4 and on the bottom 0.4, 0.4. So our z statistic is 1 this time. So for a z statistic of 1, right, remember that's a z-score of 1 on this distribution. So it's going to be right where this is. Z equals 1. And we're interested in samples that are really tall or really short on either side. So we're also going to be interested in z equals -1. And we want the area more extreme than those z-scores. So we need to look, to look up on the z table what the area is beyond z equals 1. So I did that earlier, and I got the area to be 0.1587. So about 16% of the normal distribution is beyond a z equals 1. We're also interested in the area beyond z equals -1. It's a symmetrical distribution, so it'll be the same over there. Right? And the p-value is going to be more extreme either direction, so we need to add these up. 0.1587 times 2, 14, 6, 17, 1, 3. So now our p-value equals 0.3174. We could have just wrote p equals 0.3174. Those mean the exact same thing. Okay, so we need to compare alpha with our p-value. And in this case, our p-value is larger than our alpha. So in this case, if this is what our results were like, we would fail to reject the null hypothesis. We would have an inconclusive study because our sample isn't extreme enough for us to decide that it is unlikely to have come from this population. This is the kind of sample mean that you commonly get from this kind of population, and so we can't decide that it's from a different population of taller men like we had hoped. With a p-value of 0.3174, this sample isn't very extreme at all. In fact, about 1 in 3 samples from this population are about this extreme. So it's a pretty common sample due to random sampling if the null hypothesis is true. And because it's a common sample, if the null hypothesis is true, we can't reject the null hypothesis. This is the kind of data that's actually not very inconsistent with the null hypothesis. It's pretty consistent with the null hypothesis. Remember, we just fail to reject the null hypothesis. We don't actually know if we fail to reject the null hypothesis that our sample came from this population. It could have come from a slightly different one that had a mean of 70.1, right? Because that's not the same as 70. And there's an infinite number of population means our sample could have come from if it didn't come from this exact one. So we can't decide if we fail to reject the null hypothesis that this is where our sample came from because our results are consistent with a lot of different populations.